All right, folks, welcome back. Let's pick up right where we left off with yesterday. And what I asked you to consider then is when we combine together these p orbitals from the atoms that have electrons in the p orbitals, when we combine them together to form these molecular orbitals, how do we form these here? I mean, we saw yesterday how the sigma 2p here forms. You remember the two, you had the two you had the two separate 2p orbitals. Okay? They line up along a line so that there's a line of symmetry that's lined up through them. And so we refer to that as a sigma interaction. And so with the bonding sigma 2p, we saw then that with the two of the three separate p orbitals to come together, two of them will line up. I'm sorry, the six p orbitals that come together on either side. Okay, two of them will line up. Okay, two of them will line up in a linear manner here, and because of that, we form then a sigma bonding. So this is going to be our sigma bonding molecular orbital, and that comes from the 2p. So we saw how this particular orbital forms, and so the anti-bonding one that we saw then results from the interaction of the 2p or the two 2p orbitals that are lined up along the same line as well. And so these then represent then if this represented the constructive interference of the two atoms, this represents then the destructive interference of the two orbitals. Okay? And so you get then a node right here, and therefore then we have an area where there's no electron density. Okay, and so that we saw then how we can form the sigma 2p and the sigma anti-bonding 2p. So we saw how those two form. The question is, how do these four form? How do these four form? Well, let's consider what we have here. Okay, what we have remaining then are two orbitals then that are lined up along, not a line, but they line up side by side. So remember, we had arbitrarily chosen then that these orbitals will be the two orbitals that are lined up along the x-axis. Well, we have two remaining orbitals that line up along the y-axis and two that line up along the z-axis. And if you notice here, when they line up, they do not line, there is not a line of symmetry that can be drawn through these here. I'm sorry, a straight line that can be drawn through both of these here. Instead, what we see then is that they line up side by side. They line up side by side. And when we have that side by side interaction, remember, what we have then is a pi interaction as opposed to the sigma interaction that we have here. So then you can imagine then that when these line up, and if I want you to notice here, these line up so that these are opposite in signs. These are the same signs here, and same thing holds true for the two p orbitals lined up along the z-axis. Here you have them lined up that with opposite signs. Here you have them lined up with same signs. So in this case, then we are going to find then that this pi interaction is going to be formed from a destructive, and this pi interaction can be from the constructive. So this is going to be the pi then that forms then. It's going to be a what we refer to as the pi anti-bonding. So we'll see then that this is going to be the pi anti-bonding. I'm sorry, let me go ahead and start this. And this is going to be the pi bonding that forms from the 2py axis. And here then, same thing will happen. We're going to have then a, this is going to be the anti-bonding orbital, okay, which is what we have right here. And this is going to be our bonding orbitals. And so the same thing happens here. We're going to get then two types of molecular orbitals here from the pi interaction. And again, this interaction is different from what we have here. This is going to be this interaction, the interaction that forms this is the sigma interaction. The interaction that forms these molecular orbitals here are the pi interaction, because the two atomic orbitals line up side by side instead of in a linear manner. Okay. But we still have the constructive versus destructive interference. So this is going to be our destructive, the destructive interference. This is going to be the constructive interference as well. And so remember, this will happen in both cases. Okay. And so when constructive interference occurs, we get the bonding, and that accounts for this here. And then when the destructive interference forms, we get the antibonding. So you can imagine then that these two orbitals form when the y atomic orbitals get together and interfere with each other. Okay, and so the same thing happens down here. We're going to have then the 2pz, I'm sorry, the 2pz, okay? And this will be, since this is the two nodes that are, I'm sorry, the two, these are opposites in signs, this will be your anti-bonding. So this will be your anti-bonding. Okay, and down here, this will be the 2pz bonding that forms as a result of the constructive interference. Okay, so this then ends up being the 2pz interactions. And so that's how these molecular orbitals form. And so there we have it. We have accounted then for all of the atomic orbitals that, so remember, we have then 6 atomic orbitals that go into making the molecular orbitals. We should have 6 molecular orbitals that form. And there we have 1, 2, 3, 4, 5, 6. Okay? That accounts for the 3 from this side, atomic orbitals from this side, and the 3 atomic orbitals from this side. Okay. All right. So we go and save that really quickly. Okay. So that's how we have it there. So if you look at these pictures here, you have the side-by-side interaction. So you have the side-by-side interactions of the remaining p orbitals that forms then the anti-bonding and the bonding p orbitals here. And then we see then these are the orbitals that form, and those are the p orbitals that form from each the pi molecular orbitals that form from these p orbitals here. Okay, and so again, I'm going to highlight for you what happens is it's the constructive and destructive interference of these orbitals here. So remember, these represent then the electron, the waves. Okay, and so when they interfere with one another, they will interfere either in a destructive way here or a constructive way here. And again, the key difference here is that we don't have a line that we can draw through this, but if you notice here, if we draw a line here, there's a side-by-side symmetry, I guess if you think about it in that ways, and this represents the pi bonding interaction here. So that's how those pi molecular orbitals form. Okay. All right. So with that said, let's go ahead. Okay. And let's take a look at how then the boron molecule. Okay. So with the boron, then what we have, and let's go ahead and draw this in. Okay. We have then, and I'm just going to do this here. We have, remember the electron configuration for boron, and for each boron atom is going to be a 1s2, 2s2, 2p1 on each side, 1s2, 2s2, 2p1. Okay, and so we will only, when we consider molecular bonding, okay, we are only considering the valence electrons here, and so therefore there are 3 electrons, 2 in the 2s on the other side, 1 on the 2p. So obviously with the 2s orbitals here, the electrons in the 2s orbitals here, they will form the sigma 2s and the sigma 2s anti-bonding here. Okay, and then these 2 electrons, these 4 electrons here between the 2 borons, and so remember, I want you to remember that we have to account for 6 total electrons in the boron molecule. Okay, and so these 4 here will fill in these 2 molecular orbitals here. Okay, so that accounts for 4 of the 6. The remaining 2 then will fill in the sigma 2p. And so in terms of energy then, as far as we've written right now, the sigma 2p is lower in energy than the pi 2p. And so the electron configuration then, if we were to write out the electron configuration for diboron, okay, if we write out the electron configuration diboron, then we'll have then in the sigma 2s orbital, molecular orbital, we're going to have 2 electrons here. Okay, in the sigma 2s antibonding orbital, we have 2 electrons here, and then finally in the sigma 2p bonding molecular orbital, we're going to have 2. So that accounts then for the 6 valence electrons, and so that is the electron configuration. This will be then the electron configuration for diboron. And so we need to be able to write these, folks. We need to be able to write these, and your homework for tonight's going to ask you to do that. Okay. All right. So as it stands right now, that's what we have for the electron configuration for diboron. But remember, with all electron configurations, and we're going to, with photoelectron spectroscopy, which I'm hoping we can start today, we have to be able to support these electron configurations with experimental data. Okay, and so we can collect data on the energetics, the energies of these electrons here to determine whether we have correctly placed these electrons or not in this molecule. Okay? And so if the experimental data does not support our electron configuration, we have to go back and we have to revise it. Okay? So we'll talk about photoelectron spectroscopy in just a moment. Okay, but there is another experimental. There's another quality. There's another characteristic to all of these molecules that we can use as well to support our electron configurations, support whether we have predicted correctly the electron configuration for a particular molecule. Okay? And that that data, that physical property, is what we refer to as paramagnetism. Paramagnetism is essentially the ability of a molecule to be either attracted to or repelled by a magnetic field. Okay? And there's one characteristic of those molecules that will determine then whether they will be drawn into a magnetic field or whether they are expelled from or repelled from the magnetic field. And it depends on whether they have unpaired or paired electrons. Okay? And so when a molecule has unpaired electrons, then what will happen then is it will be attracted into the magnetic field. So you can imagine this is our magnetic field here, okay, our magnetic field here. So what will happen is if a molecule like oxygen here, dioxygen, which has a set of unpaired electrons, which we will do in just a moment. We will write out the electron configurations for these molecules in just a moment. Okay, but when you write it out, you're going to see then that dioxygen has a set of unpaired electrons. As such, then it will be pulled into a magnetic field. So when that happens, then we refer to that as paramagnetism. Paramagnetism results from molecules having unpaired electrons and being attracted, being pulled into a magnetic field. On the other hand, if you have molecules that have paired electrons, they will be repelled from a magnetic field. They will be pushed out of the magnetic field, and we refer to that condition then, that situation then as diamagnetism. So diamagnetism refers to molecules that have paired electrons, and because they have paired electrons, they will be repelled from a magnetic field. So we use then the interaction of these molecules with a magnetic field to determine then whether these molecules have paired or unpaired electrons. We can use this data here to help us write down electron configurations. Okay? And so we can, how do we collect this data here? Well, let's go ahead and take a look at a very simple apparatus that sets up that allows us to do this. And this is a very simple apparatus that we can use. Okay? And so here we have a balance, just the measuring balance, that we have in our classrooms. Okay? And to that we set a sample tube, okay, and we're going to connect it to the balance here. So we connect it to the balance. We have a set of magnets here. And so what we do then is we take out our sample tube here. Okay, we take it out, we put in what we need. Okay, and then what will happen then is if the tube gets pulled into the magnetic field, it'll pull down on this balance. Okay, I mean, this is a very simple diagram of how we take this measurement, but that's how we do. So whatever's in here, if it gets pulled into the magnetic field, okay, if it gets pulled into the magnetic field, we know then that whatever the sample is going to be paramagnetic, okay, which means it has an unpaired electron, and so it's going to pull down. Going to get pulled into these are two magnets. The magnetic field is set up right here. Okay, so the magnetic field is set up. I'm sorry, let me go ahead and do this. Okay, if the magnetic field is set up right here, there's your magnetic field. So this is the magnetic field here. Okay, so if whatever's in here gets pulled into the magnetic field, if that is the case, then we know then that it has to be paramagnetic. Okay, so because whatever's in there gets attracted, it will pull down on this balance and then we'll register it. So we know then whatever's in here, if it gets pulled down, has to be paramagnetic. If it doesn't get pulled down, then you can imagine if it's diamagnetic, gets repelled, then the balance will either move up. But typically what we see then is that if it's diamagnetic, we won't see any motion of this balance at all because the sample here, the sample tube won't get pulled into the magnetic field. So what we're doing then is with this particular balance, what we're doing is we're testing for paramagnetism. we're testing for paramagnetism, and if it's not paramagnetic, it has to be diamagnetic, which means then if whatever's in this tube does not get pulled into the magnetic field, that means if the balance does not move, then we have a diamagnetic substance inside the test tube here. Okay, so that's how we test for for magnetism. We can use the magnetic nature or the interactions of these molecules with a magnetic field to determine then whether we have paired or whether we have unpaired electrons. Okay? So how are we going to use this? So let's go ahead then and let me ask you to consider this here. Okay, we said then, okay, we said then that the electron configuration, and I'm going to write it down here for you again real quickly. Okay? We said then that the electron configuration for diboron was going to be, so for diboron, okay, the electron configuration was sigma 2s 2, okay, sigma 2s star antibonding 2, okay, and then sigma 2p 2. Okay, so I'm going to ask. So let's consider this here. Okay, based on this electron configuration here, based on this electron configuration that we just drew up here, we expect then for boron. So let me just ask you to consider this then. We expect boron then to be diamagnetic. So based on this, we expect diamagnetic. Okay, we expect diboron to be diamagnetic. It has all paired electrons. Okay, so we have then a substance that has only paired electrons. We have paired electrons here, paired electrons, paired electrons. These are not unpaired electrons. So therefore, do we expect this particular, do we expect diboron to be pulled into or repelled by a magnetic field? We expect then the diboron to be repelled by a magnetic field. That is our expectation based upon the electron configuration that we came up with here and the order, the order of the molecular orbitals here. Okay. However, what I want, the experimental data shows us then that diboron will be drawn into a magnetic field. It gets drawn into, and so experimental data shows then that actually diboron is paramagnetic. Okay, diboron is paramagnetic. So my question to you then is this: how is that the case? Okay, how is that the case that if this is what we expect, how can we have a compound in boron that's paramagnetic when everything, all of these electrons are paired up? Okay, how do we go about explaining that? Well, remember, paramagnetism means then that we have to have a pair. We have to have two of these electrons that are unpaired. Two of them have to be unpaired. Okay. Now, remember when we talked about filling in and writing out the electron configuration for these molecules here using molecular orbital theory, we're going to use the same concept that we used in writing out the electron configurations for the atoms. We start out lowest energy levels first. We fill in the lowest energy levels. Okay, now the maximum number of electrons that can fill in a particular energy level is going to be 2, or a particular orbital can be 2. And then if they can spread out, they will. And it's that spreading out of the electrons in the atomic state that accounts for the single electron. Okay, and so let's use that to understand how this works. Now there are 6. So remember, we had to count for 6 electrons. Okay, so we expect then that the lowest energy orbital to fill in first, and we have that right there. And then when 2 fill up, then there's going to be 4 more. Okay, so 2 more fill in this particular energy level here. So that makes sense. Okay. And then if this diagram is correct, then we expect then 2 electrons fill in here. And so that cannot be correct because our experimental data shows then that diboron is paramagnetic. So something has to be going on right here that is problematic for us. Okay? And so what is that something, and how do we go about explaining that? Okay, how do we go about explaining that? Well, let's go ahead then and let's consider this. Okay, so B2S diboron has to be paramagnetic, which means then we have to have a set of unpaired electrons in these molecular orbitals. The way it's set up here, we can't have that. the way that that we've predicted the electrons should fill, and this energy diagram for the molecular orbitals here can't not be correct. Okay? So what we do then is we can propose, okay, a way that this can split up. How can this split up? Well, it can split up, you can imagine it as if it somehow fills in this orbital first. Okay? If it fills in this orbital first, then you would have one move here and a second one move here. But how in the world can we get these two to fill in before these two? Before this one? How can we fill in these two orbitals before this one? Because remember, the Aufbau principle tells us that electrons always fill in lower energy levels first. Okay. Well, the idea then is this. Okay. If we can flip that around, that is, if the actual model has then the pi 2p lower in energy than the sigma 2p, then we can fill in these orbitals here, and Hund's rule tells us then that the electrons will split up, which they do here, and there we have it. There we have two unpaired electrons, which would explain then the paramagnetic nature of boron. Okay. All right, that's a whole lot to kind of take in there, folks. Okay? And so with the molecular orbital theory, so to sum things up here for you, okay? So with the molecular orbital theory then, okay, what I want you to understand then is that there are two possible energy diagrams for the molecular orbitals. Okay, there are two possible energy diagrams, so two possible ways that we can align up the electrons. The first possibility here is that what we've already discussed at the very beginning, where the molecular orbitals form, okay, and then the sigma 2p orbitals are going to be lower than the pi 2p orbitals. However, taking into consideration then the magnetic nature of particles, there is a second possibility for the molecular orbital, the energy of the molecular orbitals, and that is one in which the sigma 2p switches place with the pi 2p. Okay, so when we write out the electron configurations, and I'm going to start doing this in just a moment, when we write out the electron configurations, we have to decide between one of these two here. Which one is going to be the correct one? And what are we going to use to determine which one of these two will help explain and give us the correct electron configuration for a particular molecule? We will have to use then the magnetic nature, paramagnetic versus diamagnetic nature of the molecule, and then we have to use what's called photoelectron spectroscopy. And so the reason why I want to do this is that it will allow us to start our discussion of photoelectron spectroscopy and understand how we can use that information and to determine the correct electron configuration for a particular molecule and for atoms as well. And so photoelectron spectroscopy is a very powerful spectroscopic technique. And you'll learn much more about spectroscopy as you move forward in chemistry, but spectroscopy is our way of indirectly looking at what happens with the atom and with the electrons in the atom as well. Okay? All right, so let's go ahead and let's practice this. Okay, so we have two options here. Let's go ahead and let's practice this here. So let's keep this in mind. Okay. All right. What we're going to be doing here is very similar to what we did, and I think this is a chart that's similar, familiar to some of a few of you who've had me before. Okay, when we write out the electron configurations for the molecules, okay, which we'll do, we're essentially going to be filling in orbitals. We're going to be filling in atomic molecular orbitals, which is essentially what I did for my folks in my chemistry classes last year. Okay, that is, I gave them this diagram here, which gives the energy levels for the different atomic orbitals. And what we did here then is we wrote out the electron configuration for, we figured out how many electrons carbon has. Okay, so carbon has total electrons, six electrons. Okay. And so then what we did was we started filling in this using the rules, three rules that we used to fill in electron configuration. Okay, so carbon has 6 total electrons. Okay, and so therefore then the orbital, the atomic orbital at the lowest in energy is the 1s orbital, and so we fill that in with 2 electrons. Okay, so Aufbau principle tells us that 2 electrons get filled in here first. Okay, and then we have 4 more to go. So then therefore we jump up to the next energy level and we fill in 2 electrons there. Okay, so that will fill in the 2s orbital here. So remember, in each space, a maximum of 2 electrons, they have to flip their spin according to the Pauli exclusion principle. And then once you fill that in with 2, you jump up to the next energy level. Okay, so here the 2s orbital now is filled. We have 2 more electrons to account for. Those 2 electrons will fill in the 2p orbitals here, and they will spread out according to Hund's rule. Okay, so that then you have 2 unpaired electrons here. You have 2 unpaired electrons. So that's how we were able to come up with the electron configuration for carbon, which is 1s2, 2s2, 2p2, and from this diagram here also, that's how we know then that we have then in our valence in our valence shell here, we have 1 pair and 2 unpaired electrons. Okay? So we have 1 paired and 2 unpaired electrons. Okay, 1 paired, 2 unpaired. Okay, that's what we did back in first year chemistry. Okay, with this very simple diagram here. We will be doing the exact same thing, folks. We will be doing the exact same thing. Okay, I'm sorry, with molecules. Writing out the molecular electron configuration, we're essentially doing the same thing. But this time then, instead of using atomic orbitals, we're going to use the molecular orbitals here and here. And so I'm going a little bit over time here a little bit, but make sure you understand that tomorrow, what we're going to be doing, we're going to account then for all the electrons. We have to make sure we count all the electrons, just like what we did with the single carbon atom. We had to account for all 6 electrons in the atom itself. In the carbon dicarbon here, in this particular molecule, we have to account then for a total of 8 electrons. Why? Because remember, we're only counting the valence electrons for each carbon. So what I'm going to do tomorrow for you is we're going to work on these electron configurations. Let's hold off on the homework for tonight for a little bit, but this is what we have to be able to work on. Okay, we need to be able to write out the electron configurations and be able to support our answer using the magnetic properties of this molecule here, and also the photoelectron spectroscopy, the data that we collect from that, to support whether which one of these electron configurations or which one of the energy diagrams here would be correct for this particular molecule. Okay. And so we'll start that tomorrow. And unfortunately, we only have 20 minutes of a lecture time here. And so, you know what, so what we'll do is we'll start this tomorrow. And then what I'd like to do then is, I want to take a little bit more time. So I'm going to take about 30 minutes of time tomorrow. I'm going to go over a little bit in order to try to give us enough practice in doing these electron configurations, and then hopefully start photoelectron spectroscopy as well. And then same thing, I'll be posting videos for you on Saturday and Sunday as well, so that we can get caught up. Please watch those, okay? And then hopefully we'll round out with the discussion of Beer's law next week, okay? And I'm sorry, what we'll do is I'll quickly go through a few things you'll need to know in chapter 10. And then I think chapter 10 should be fairly straightforward for you, but please take a look at that, okay? And so the only new chapter 10 is going to be fairly familiar to you, so you'll be able to recognize that. And so the only really new topic that we'll have to talk about before the AP exam would be Beer's law, okay? All right, folks, so I will see you tomorrow. Have a good day.